Hello and welcome to the section 7.4 lecture. Today what I want to do after I get this set up, sorry about that, but today what I want to do is get us going on some two variable inequalities. That's our goal for today, is to be able to graph two variable inequalities. Let's go ahead and look at what I mean by that. If we have a number line and we're saying we're graphing x is greater than -3, -1, -2, -3 right there, we would call that an open circle, and somehow we'd be shading where the numbers are bigger over here to the right. Okay, that would be our goal on a number line. Now when we turn that into what we consider as a two variable inequality, even though there's no y involved, we're still going to do kind of the same thing, but what would this look like? An open circle and shading to the right. What would that look like on a two-dimensional graph as opposed to a one-dimensional number line? Well, since we're looking at something that can't be -3, we have to denote that somehow. We do that with a dashed line through -3. So a dashed line through -3, and then everything shading to the right. Find the best way that you can make it an obvious shade, but not have to, fill in the whole thing. I like using diagonal lines to represent that. But what are we really doing here? We're looking for all coordinates that have an x value greater than -3. So we can think of some concrete examples right here. This point is 3. So, wow. Learn how to do our coordinates, why don't we? But this location, this point is -1, 3. Its x value is greater than -3. Okay, and same thing is true on all these points, even down here. This point at 1, -2 has an x value of 1, which is again greater than -3. Okay, so it's all these points over here. And if you notice, on the other side, we have coordinates like this one here at -4, +2. And this x value is not greater than -3. Okay, it's less than -3. I guess I wrote that wrong down there, didn't I? That was a -3 I was talking about. And so this one is less than -3, so it doesn't work. Okay, so when we were shading number lines, we were cutting a number line in half, basically. And obviously that's kind of a judgment call. Is it really in half? It is. You're shading one side of it, not shading the other side of it. The same thing's going to happen in two dimensions. We're going to shade one half of our graph, even though from what I have here, this is way more than a half. But we have to remember that these graphs go on forever, and they're basically, infinite. And so they can't really be cut in half. But for our purposes, we think we want to cut this graph in half, and we're going to shade one side of it and not the other. And then we really have to determine, can it be that value in question? Okay, and on this one, we had an open circle, and that's going to give us a dashed line. If we had a closed circle, we would make that a solid line. So there's about 4 steps that we want to follow. And when we try to graph two variable inequalities, the first thing we'll look for is it solid or dashed. And it's going to be a solid line when there's the or equal to, or in other words, less than or equal to or greater than or equal to. Then we'll have a dashed line otherwise, just in the less than or greater than. Then we'll graph the line, mainly hoping for slope-intercept form. Okay, maybe you have standard form, maybe you have to do it that way. No matter what, that's what we're looking for. Step 3 is test, and we want to test a point not on the line. And remember, we did this a little bit in class where graphing these, I would say, well, what happens if we choose 0? You know, we kind of thought about, let's go ahead and test 0. Is 0 greater than -3? Is 0 greater than -3? Yes, it is. Okay, that works out. So we shade the side that 0 was on, and we said anything on 0's side of -3 worked, and so we shaded all that stuff. We're going to do the same thing, but with 2 variables. With 2 variables, we need to plug in an x and a y coordinate. And see if we get a true or a false statement. Okay, and then we're going to shade half the graph. I'm not going to write anything else on there just to save our hands a little bit. But in essence, if we get a true statement, wherever that point is, again, it shouldn't be on the line. So wherever that point is, if that point is true, then all points on that side of the line are true. If that point is false, all points on the other side of the line are true. And so we would shade that other side of the line. Let's go ahead and give it a shot. And we're going to kind of follow our steps here. Number 1, we want to see is it solid or dashed. Okay, since it's just a greater than, it's going to be dashed. So I always do that first because I don't want to graph my line and then have to go and erase it if it needs to be dashed. But you could do that. It's a little bit harder for me. 2, graph the line. I'm thinking about y equals 2x plus 1. And that's in slope-intercept form. So I'm going to 1 and going up 2 and over 1. Up 2 over 1. I'll even go the other way because I'm going to have to freehand this in order to make it a dash line. Okay, so dashing that line. And so this is my step 2, graphing the line. And I've got it on there. And now I want to pick a point to test. Whenever I can, I like to test 0, 0. And the reason I say when I can is I have to make sure that 0, 0 is not on the line. And I like to note where my test point is. It's not on the line, so it's okay to test. And so what do I do for that? I'm going to plug 0 in for y, and I'm going to say, is that greater than 2 times 0 plus 1? Well, 2 times 0 plus 1, that's going to be 0 plus 1 or just 1. That is not correct. Okay, that is a false statement. So everything down here is false. And it sort of has a I guess, dichotomous solution or a relation. It's either everything on that side is true or everything on that side is false, which means that the other side is the opposite. So everything on that side is false. That means everything on this side is true. Okay, any point over here would work, and we don't have to go hunting for one of those and find a true solution. We just, at this point, get to say everything over here is going to be true. So we shade that side. Again, find a decent way to present your solution. It doesn't have to be shading like this, where we're shading everything over here, because that would get a little bit overkill. And especially when I'm having you borrow pencils, it seems like it's just going to waste more pencil lead, right? Okay. So you don't have to go that far. That's a little overkill. I'm fine with that. Okay, just make it obvious. Obviously don't draw on the lines that are already on the graph, because I know pencil lead on black is hard to see. Okay, but that's my answer. That's my step 4 right there, is to shade that side. Okay, let's go ahead and look at a couple more. I want you to try these. Go ahead and pause the video and give them a shot. Okay, hopefully you had a chance to do that and we're able to go at it. This one you should have found is a solid line, and it starts at -3, and it goes up to and over 3, up to over 3. And since it's a solid line, I'm going to go ahead and leave it at that and get a line out here a little bit quicker. That's the quicker way for me to do that by far. And this is definitely a time that we want to make sure that we graph our lines all the way through the graph, because I've got a shade all the way through my graph. Okay, since 0, 0 is not on my line, I'm going to test 0, 0. Again, if I can, I want to, because of the great things of multiplying by 0, that multiplying by 0 does. I don't want to write y, I want to write 0. So is 0 greater than or equal to? And when I'm saying is 0, that's why I'm putting that question mark up there. I'm saying, is it true? 2/3 times 0 is 0, minus 3 is -3. That is a true statement. So that means everything on this side is true. So we find a way to shade that. And if you want to try to get as close to that line as you can, even better. Okay? Or even if you want to go both directions, I'm fine with that. Okay. All right, this next one, maybe you had a little trouble with it. It is in standard form. So graphing it's a little bit different. It is a dashed line. And so graphing in standard form, we use our cover-up method. So I can cover up the x term, and I get 3y. I'm thinking of it in the equals sense, but 3y equals -6 or +6. Dividing by 3 on both sides, I get that y is 2. Then covering this up, I get 2x equals 6. It's been a long day. Dividing both sides by 2, I get x equals 3. Okay, so there are my 2 points. And, you know, I know I didn't find my slope, but having these 2 points gives me a slope. This one looks like it goes down 2 and over 3, and I need to know that because I have to dash a line all the way through here. So I'm just going to try to keep that going a little bit. It almost acts like a dashed line, just having all these points. But in practice, it just makes it a little bit easier. I can't bend my hand and try to do it that way. So we're just going to try to dash our line out. Again, do the best you can with what you've got is all I can expect. And again, I'm going to test 0, 0, or I would test 0, 0. I'm going to try something else, okay? I know that I can't pick anything on the line, but I can pick something like, and maybe you tested 0, 0, and in standard form, if you can test 0, 0, it makes life really easy. But I'm going to test something random, like let's go 4, 4. Right, so if I look for it 1, 2, 3, 4, 1, 2, 3, 4. I'm testing that point right there, just to show that we can. Okay, I'm going to test 4, 4, and I'm going to show that this is not overly difficult, but definitely more difficult. So the question is 2 times 4 plus 3 times 4 less than 6? You should have a feeling that it's not. And you'd be correct, because 2 times 4 is 8, plus 3 times 4 is 12. Is that less than 6? Is 20 less than 6? No, it's not. That is a false statement. So that one's false along with everything else over there. So if you did test 0, 0, you probably got a true statement, which is all fine and dandy. Okay, and that's the shading that we get. All right, let's look at this application practice. So this is a good kind of multi-step problem to deal with. Let me make it to where you can read it. Okay. It says that you're on a treasure diving ship that is hunting gold and silver coins. Objects collected by the divers are placed in a wire basket. One of the divers signals you to reel in the basket. The reel will break if more than 50 pounds, if there's more than 50 pounds in the basket. If each gold coin weighs about half an ounce and each silver coin weighs about a quarter ounce, what are the possible different amounts of coins that could be in the basket? So first thing that we need is how many ounces are in a pound. That's kind of a hidden part of this. And to be honest, in previous renditions of this, I don't think that I've dealt with that. So you can always check if you're unsure. Oh, you can't see it. But just as I figured, 1 pound is 16 ounces. Okay, so we're actually just going to do this problem in. We'll change it into ounces because that's what we have. Nice breakdowns for our gold and silver coins. But what that means is if I have 50 pounds, and I'm just doing it on that same thing, that's 800 ounces. Okay. So the weight cannot be less than 800 ounces. So 800 is kind of our operating number here. It has to be less than 800. And it says if there are more than 50 pounds, so it can actually equal 50 pounds or 800 ounces. And just to remind you that this is 50 pounds in ounces. So that way, I don't have to come up with a smaller decimal for my weight of coins. Okay, and then it also kind of feels like these X and Y values are really made in the ounce category. Okay, so let's go ahead and take a look at this. I know that the weight, and this comes into play a lot of times in word problems. The overall weight from all the gold coins I put in there. So I'm gonna kind of define some variables here. We're gonna let G be our gold coins. And more specifically, our number of gold coins. And we're gonna let S be our number of silver coins. Kind of running everything together here. Okay, and we have a couple of things to get dealt with. The total weight from all the gold coins is going to be the weight of one gold coin times the number of gold coins. That's a huge thing in math. It's used in almost, I would say, at least half of all application problems, and it's kind of a big deal. So a gold coin weighs about half an ounce. So half an ounce times the number of gold coins will be the total weight from the gold coins. And then I can add the quarter ounce times the number of silver coins. And that's going to be the total weight from all the silver coins that are in the basket. So this is now my equation that I'm going to be working with. And trust me, it's a lot better to do it in ounces than pounds because you're looking at half of it. You're looking at the weight of a gold coin being a 32nd of a pound. Okay, and you're just going to have some ugly decimals or difficult fractions to deal with. So we're taking that off of our plate a little bit. So let's go ahead and look at this. Number one, it's going to be a solid line because of the or equal to. To graph it, I need to use the cover up method. So I'm going to cover up gold, and I'm going to kind of set this up as this will be my gold axis, this will be my silver axis. Okay. And so let's go ahead and look at covering up gold. So I have 0.25s equals 800. So I'm going to take that 800 and divide it by 0.25. Let me grab a calculator for us. So I'm taking 800 divided by 0.25. 25. And I get 3,200 as a intercept, as technically an S-intercept. For my G-intercept, I'm going to cover up the 0.25. So I'm going to take 800 divided by 0.5, and we get 1,600 for a gold intercept. Okay. And again, this was a solid line because of the or equal to statement. And then test a point. And always on this one, I would test 0, 0, as long as it doesn't go through it, because 0 times 0.5 is 0, 0 times 0.25 is 0, and then you're just asking, is 0 less than 800? And it is. Okay? So anything down in this region will be passable. And obviously, negatives don't really make sense here. That's why the graph is drawn how it is, because I can't put negative coins into the basket. All right, but that's really all we have for today. So coming from this, what are the possible different amounts of coins that could be in the basket? Anything that would fit into this region. Okay, it's really hard to say in words how it can be, but you know that's kind of the idea, is that we're finding a way to display our solution, being that we can have 3,200 silver coins and no gold coins, all the way to 1,600 gold coins and no silver coins. But even that, like, well, what if I had less silver coins but more gold coins? You could find specific places where that will work, but it won't be everywhere. Okay, so this is kind of the best way to display your solution. They could say, hey, look, we found 2,400 silver coins and 800 gold coins. Okay, 800 and 2,400, that's going to break the real. Okay, that's not going to work. So, I guess I wasn't even on 800, was I? Still, regardless, that's still going to break the real. Take a couple hundred of those gold coins or silver coins out of there, and you'll be good to go. Okay, that would be the talk that you would have with the people working on that diving trip. Okay, so that being said, make sure that you get the mastery challenge done. As far as practice problems, I guess we can take a look at those. I think you're good for, there's 9 of them there. Let's go with evens. And I'm going to say for practice, let's go with evens. I think that would be a good set. And then for application problems, I'm going to say 1 and 2. So kind of all application. Okay, and then you can watch the application walkthrough for that to get a better idea of how to do it. Anyways, that being said, I hope you have a great day, and we will see you in class.